Hi everyone, my name is Keisha Hunsucker, and me and Jaime are going to be presenting our unit plan titled Linear Relationships in Geophysics, Soil Moisture Investigation. This is a 5-lesson unit designed for 70-minute class periods that connects Algebra 1 with real-world environmental science. As you can see here are the standards that it aligns with. It aligns with next generation science standards as well as Common Core mathematics with a focus on a linear unit. And by the end of this unit, students are going to be able to write linear equations from data tables, interpret slope and y-intercepts in real contexts, create and analyze linear graphs, and use these to make predictions.
Okay, I'd like to talk about the career connections with our lesson. So our lesson connects directly to real-world STEM careers. Katrina Burch is a research geophysicist who studies how ice forms in soil and how that impacts buildings and the environment, especially in cold places like Alaska and Antarctica. She works at the CREL, the Cold Regions Research and Engineering Lab, where I was fortunate enough to visit, learn, and perform research with her this past summer. Careers like geophysicist, civil engineer, soil scientist, seismologist, data modeler, and more all use math and science to solve real-world problems, just like in this lesson. All right, next I'd like to go over the engagement section of our lesson. This lesson introduces students to geophysics by exploring how we measure soil moisture without digging. We start with a hands-on demo using dry, damp, and wet sand to spark discussion. Then students watch short videos on near-surface geophysics and soil moisture. They take notes and explore interactive simulations showing how water moves through different soils. Finally, they will model the data using linear equations to understand how math helps us see underground. Now let's talk about the explanation phase of our lesson plan. In this lesson, students apply what they learned about soil moisture and geophysics by solving real-world problems using linear equations. They will work with scenarios like estimating moisture from resistance or depth from wave speed. Students will write and solve equations, justify their steps, and interpret results in context, while also exploring the assumptions and limitations of using math to model real-world science. Next, we will elaborate. In this group project, students apply their understanding of linear equations to real soil moisture data. They choose two variables, create a linear model, graph it, and use it to make predictions. Then they will interpret the slope and y-intercept in context, like how resistance actually relates to moisture. This collaborative work helps students find the connection between math and science, and it helps with concepts and communicates their findings visually.
Day 2 is the core of exploration phase, where students are going to be translating real soil measurements into mathematical models. They work with 3 measurement methods, which is going to be electrical resistance, sound waves, and radar. Students are going to plot data points, calculate slopes, find y-intercepts, and write linear equations. For example, they discover that as soil moisture increases, electrical resistance decreases predictably, creating the equation R equals -5m plus 450. They're going to also have independent practice similarly with sound waves. This hands-on approach is going to bridge concrete simulations from day 1 with abstract mathematical modeling, making the connection between science and algebra very explicit. And lesson 5, which is for the last day, is our culminating assessment, and it has students present as geophysics consulting teams to real clients like farmers and city planners. Groups demonstrate their linear equations, make evidence-based predictions, and provide actionable recommendations. They'll have time to finish up their projects, and then they will present it to the class and do some reflecting. This authentic performance task assesses both mathematical proficiency and communication skills while reflecting actual professional practice. Individual reflection ensures students connect their learning to future applications and STEM career possibilities. Overall, this unit aims to transform traditional algebra instruction by embedding it in meaningful scientific contexts that students can connect with to the real world. Thank you so much.